Can everybody see this? All right, I'm getting head nods. Cool. So this is Rust Los Angeles meetup. We're still virtual and online. And I know it's been a couple of months since we've been here, but looking to ramp things back up and do this monthly again. Cameron and I got busy. Myself being, if you haven't met me before, my name is Drew Arridge. I am the organizer. I took over from Herman about a year or two ago, and I kind of mega formed two Rust groups with me and Cameron, who is running another Rust LA type meetup in the absence of Herman's meetup. And most recently, and the person you can thank for bringing us back is Phil Markgraf, who was one of our previous speakers, who has had some awesome stuff to say about Rust and has spoken at a number of different conferences. Really fantastic topics. So he's our new co-organizer. He's not from Libretto. I missed to copy paste probably a bunch of these different things. And yeah, from there, I think the important thing actually is to let you all know that you can get involved. And if you want to give a talk as well, you can do that. We have a website, thanks to Cameron, called rustling.la. And if you're ever thinking about giving a talk or you know somebody who might want to, you can go right to that website and you can actually fill out just a short little Google form about what you'd like to speak about, the format that you'd like to use. We're interested in all kinds of formats and anything that we can learn more about Rust. If you ever want to help out organizing or have any other specific questions, you can reach out to me directly. That's my email. Some of these sponsors are probably old, but thank you to Game Breaking Studios, who's my company, who's paying for this Zoom chat every year. And there are a number of different companies that are hiring for Rust. AirChat is one of them. I'll post this in the comments. I'll actually probably share out a larger list of folks that are hiring in the area in case people are interested. I saw there was kind of a comment from, I think it was Singularity 6 is a game studio in the area that's using Rust for some of their online services and things like that. So actually a surprising kind of uptick even in the area of different companies using Rust professionally. So we've started with the intros these times are off by an hour, at 8:05, and we'll get right into the talk. Once the talk is over, whatever time that is, if it's if it's 15 minutes, if it's 45 minutes, whenever the talk's over, we can kind of have an open discussion. And it doesn't have to adhere super closely to this, but normally we'd have 2 breakout rooms. With the group this small, we can probably all just stick together. And I don't know why it still says Microsoft there. That is old, but without further ado, I believe it's Dzmitry. Why don't you go ahead and take over and tell us about processing shaders in Rust. I'll stop sharing.
All right, thank you for introduction. Hello, everyone. I'm just going to present something myself. So my name is Dzmitry, and I currently work at Mozilla, where I'm in the graphics team doing web render and leading web GPU efforts. Previously worked at Rockstar Games on a few interesting titles, and I'm heavily involved in Rust ecosystem for the past 9 years. I've seen it all, and I would like to share some of that experience, in particular about shaders, with you today. So let's dive in. There's going to be a few different projects mentioned and a few technologies. It requires some sort of a background in graphics. If you don't understand something, we'll be happy to clarify later. So we'll first describe the use cases of how people today in Rust use shaders. We'll go into the solutions that we developed, and then after that, we'll show how it all ended, or maybe not ended. We'll see. First, it's what is a shader? Basically, it's some code that is run on the graphics processing unit as opposed to central processing unit. And we typically talk about shaders running for each vertex of your mesh or for each little pixel of your output screen for each primitive. This is how a particular fragment shader looks like, just samples some textures. If you don't know what the shaders are, you're going to have a tough time. So I hope you have some understanding. First part, the use cases. All of the shader works today is based on C. And that applies to both the languages themselves. The GLSL, HLSL, and MSL are all C-based shader languages. And it applies to tools, because the two biggest tools in C are, or at least all the biggest tools are in C. It's FXC, DXC, and GLSL compiler, and SPIR-V cross are all written in C or C++. So when you start using Rust, you typically get targeting the OpenGL 3.2 or GLES 3.0. You run with some OpenGL wrapper and you just want to draw a triangle. That's the basic idea. And you may want to do some pre-processing to replace like attributes keyword by in and put the version in and so forth, some basic things. The issues you will be facing is poor support for OpenGL, because OpenGL is dying. Honestly, it's no longer a first-class API for a long time on Apple ecosystem. It has never been a first-class API on Windows ecosystem. It used to be such on Linux and Android, and those two are fully switching to Vulcan now. So nobody wants OpenGL to be the thing the next game is written, basically. If you want to debug it, you're going to have a hard time as well. It has a lot of bugs still, even though it has large history. In particular, parsing GLSL shaders appears to be difficult. So every shader interprets GLSL, every vendor interprets it somewhat differently. We've seen a lot of issues in WebRender, and I put the link down in the slide, like if-else conditions, switches, and all sorts of things are getting miscompiled in GLSL. So you say, okay, I don't want duplicated stuff. I want all the new hot things, which is, as I mentioned, Vulcan. It's the open standard from Khronos, effectively a successor to OpenGL. And you say, okay, I'm still going to write GLSL because you can't write the native language of Vulcan, which is SPIR-V directly. It's a binary format. So you're going to write GLSL, but in a special format, which is a Vulcan flavor. You're going to compile it, or we're going to get to it. So you're going to run using some of the Vulcan wrappers, like Ash is very popular, or Erupt, or Volcano. You're going to be targeting SPIR-V, which is in binary format, inspired by LLVM, and standardized by Khronos. It has a text form that is used by tools, but the text form is not standardized. You will see it in the debugger, for example. People often assume that since it's an open standard from Khronos, and it's a binary format, it must be great to be machine processed. So tooling, you will need the GLSL lang, or a library that wraps it from Google. It's called Shader-C. With this library, you will compile SPIR-V out of your GLSL sources. So here comes the issues. The GLSL lang is a pretty big C dependency, and Vulcan that you're targeting is not going to run everywhere. This is the timing graph of a build I just had a few days ago of Volcano examples, and you're not seeing the whole graph. The whole graph is going to be 5 screens to the right because this yellow line is going to be that long. You can see it's 550 seconds. So if you happen to be in that situation, you are in trouble. And the situation here is basically that Shader-C tries to find a pre-built GLS lang, and if it's not able to find it, it builds it. It tries to find it, and it's typically coming from Vulcan SDK. So if you are an engine developer, you typically have that and you're totally fine. If you're just messing with a game and trying to tweak it to shape, maybe you don't know what the Vulcan is, and you're going to have a hard time because your game will compile, at least for the first time, for a long while. And I've been in that situation many times, especially on Mac OS, where Vulcan SDK is not that ubiquitous, I guess, as on other systems. I'm going to share a few horror stories about C dependencies, and this is the first one. C dependencies are notorious for bad threading because it's hard to make threading safe in C. It's just very hard. So GLSL had this issue that forced a shader C to basically wrap the whole thing in a big fat mutex and make it completely unparallelizable. It is fixed since then, so it's not an issue right now, but it's just a sign of a more general thing that happens to C dependencies. Now, I mentioned that Vulcan is non-portable, and you may be wondering, what do I mean by that? It's the open standard, it can run everywhere. So Vulcan is 5.5 years old now, since it's released, and you can technically run it on many systems, but it's not the portability in a strong sense. So if you're using some of the libraries to run Vulcan over macOS, for example, you're running over a big C-based translation layer that is non-Vulcan conformant. So no guarantees at all. It can blow, it can render something incorrectly, and you're not effectively running Vulcan if it's non-conformant. That's what I mean by non-portable. This is a map that I probably spent most of the time preparing for the presentation by drawing. It's showing the continents as the platforms, and the dark spots is where Vulcan currently covers. So we know that most of the Linux is covered. It's really great on Linux, no doubt on that. On Android, it's getting there. It's still, I think, around 50% Android devices, but all the future Android devices there are going to be forced to support Vulcan by Google, and that's a great thing. But if we're talking about today, it's still not quite there. You will still need Opengl to run on Android. Then goes Windows, and it's an interesting situation on Windows because people think typically that Vulcan is on Windows, and it's great. So yes and no. Vulcan is on Windows by the wish of the hardware vendors, who may or may not include Vulcan drivers in their distributions. Windows itself does not care at all. Vulcan is not a first-class API on Windows. They just allow it, but they don't make it nice for you. And some of the vendors think that it's not worth porting the Vulcan drivers on Windows system, like Intel, Haswell, and Broadwell, which takes a big chunk of Intel integrated GPUs. They have perfectly working drivers, conformant on Linux, but completely absent on Windows. So if you're really trying to be portable, then Windows Vulcan is not quite there. Maybe in 5 years, when these platforms are deprecated, you will be there, but not today. Finally, there is an Apple Kingdom, and all of their systems do not support Vulcan. The only way you can run Vulcan there is by some sort of a translation, which there's been work in Khronos to standardize the translation, and it's still ongoing. It's still not there. Now you say, okay, I can't totally use Vulcan. Let me use the APIs directly, maybe via the translation layer. Maybe I'm just going WinAPI.-rs or Metal-rs and Ash, and I'm just doing everything myself. I'm a superhero. So let's suppose that. You still have this problem that you wrote shaders in GLSL. So what are you going to do there? You will have to use SPIR-V cross. That's the library most used up to date for translating shaders. It's a fairly complex library. It's great in some sense because it supports all of the different backends. It supports MSL, HLSL, GLSL. It's quite powerful though. And if you're looking at, say, Dota on macOS, then it effectively ships SPIR-V cross in it in order to translate shaders. So SPIR-V cross takes SPIR-V. So you'd still have to use the GLSL compiler to produce SPIR-V, and then call SPIR-V cross to produce the platform-dependent shaders. It's another huge dependency. We are going to show how it's also slow. And goes the core number 2. If you're linking a C library and any of the objects start with a crate name, you're busted. Rust doesn't like that for no reason at all. And this feature, we wasted lots of time discovering that, and it's still not fixed. So prepare for a surprise, unresolved symbols waiting for you. And this happened with SPIR-V cross. It's not an out of thing example. This is precisely happened with our wrapper for SPIR-V cross, because SPIR-V cross has some of the object files that are called SPIR-V cross. Okay, the next one. C libraries may want to use a different standard library for C++. So what happened is their SPIR-V cross's understanding of what the standard library is diverged from what Rust CV8 thinks that a standard library needs to be. And nobody complained. Like, you depend on those both, they compile, you run, and you crash into like horrible call stacks without understanding of what's going on there. So this is an issue, again, that nobody bothered to fix yet because it's by design. It's an issue by design. It's a great thing. So don't face that. Finally, there's a number of issues that are happening if your project is linked as a C project, but it uses a Rust library, which uses a C library. An example is Gecko. Gecko uses a lot of Rust libraries, but it's mostly C still, and Rust libraries may depend on the C libraries in turn. So it has this transitive dependency, and the complication there is that your Rust compilation toolchain has to propagate all the flags for the C linking and compilation down the road, and it's fairly troublesome. Okay, there's a special place in the ecosystem for people who just want to write Rust. People from Rust GPU, they decided that they don't need GLSL. They just want to converge all of the code into a single perfect language, which is Rust. So I think the idea is interesting, and they are definitely worth mentioning here, but I haven't used it myself. As far as I understand, you are limited to build time shaders. Like, you can't just compile at runtime unless you ship Rust compiler with you, which is not a great option. So not all of the uses of shaders are fine with build time. If you're fine with it, go with it. But it's not going to save you, because you still have SPIR-V on the output, and you still have to produce platform-dependent shaders with SPIR-V cross. Now, let's talk about some of the projects. This is the Geofx Portability project, which implements Vulcan everywhere, and it's a part of the Vulcan Portability initiative. It's something that we did. We just wrapped Geofx RS into a Rust API, which implements Vulcan. And we tested a hell out of it on Dota and Dolphin Emulator and Quake 3. We accept, as a Vulcan implementation, we accepted SPIR-V, and we had to translate it to everything. So for the longest time, it used SPIR-V cross again internally to translate the shaders. So here comes one of the runs on macOS where we translated SPIR-V to MSL. It's probably the worst example I could find, because that's the only way to prove my point. It's not the average example, but that's some time frame of like 5 seconds of running the game, a real game, like Steam version of the game, basically just hooked up to use Geofx portability instead of Molten VK, which is ships with. And of those seconds, 3.74 seconds at the top, you can see are spent. Inside, it says libmoltenvk. We just had to rename or symlink Geofx portability because Dota expects this name. So this is what's spent inside the portability library, 3.74 seconds. And the top consumers of those time are all SPIR-V cross. Look at that, the selected line, SPIR-V cross, down below, SPIR-V cross, SC internal, also SPIR-V cross. So in total, like quarter of time we spend over those 5 seconds are in shader translation. I think this is entirely nuts. This is just crazy. It shouldn't happen. And bear in mind that the shaders were all heated up in the driver cache. Like, we are not spending time in Metal here. We're spending time in SPIR-V cross specifically to translate them. So this worried the hell out of me because I wanted to benchmark Geofx portability and make it faster than Molten VK. And I don't know if they do anything to make it that faster, but for us, it was a hell of a slow thing to depend on. So how am I saying the SPIR-V cross can be bad now if it's a library by Khronos? Well, it's a library hosted by Khronos, but Khronos does not make libraries. That's the very important thing to understand about Khronos. Khronos makes APIs, standards. Khronos does not make tools, and they cannot have the scope of work to make a tool for any of the groups. So SPIR-V cross is just something that emerged out of the work of some of the people who were involved in Khronos, and they felt that it's important, and they contributed to it. And it's great. It happens on the Khronos space, but it's not a Khronos project. It's just a project Khronos supports, basically. We looked into it. We found it unacceptable for our needs. Google looked into it. And for their web GPU implementation, they decided to implement a whole new stack, which is called Tint. They basically failed to use SPIR-V cross as well, even though the task that they want is essentially very similar. Get shaders in one shape and translate it in all the other shapes. So that is telling something, I think. What we failed to do, we tried to make SPIR-V cross fast. First of all, we wanted to reuse the AST, that when it just loads the shader from the binary, it builds that internal representation, which they call abstract syntax tree. And it takes time. And we just thought, when you create the shader, why don't we keep it and then use it for all the pipelines from the shader? Well, who would have guessed? In C, it's so concealed that you can't trace all the places where this AST is modified. So we tried that and we failed because SPIR-V cross kept changing the AST. It wasn't immutable. There's no way to properly express. I guess they could sprinkle the consts everywhere, but they didn't. So we failed to do that, and we had to rebuild the AST on each pipeline stage. And whenever we needed more features that weren't supported, because like you can't translate shaders in isolation. It must be done in the tandem with the platform abstraction that you use. So if the platform abstraction wants to use metal argument buffers, you need the shader translation to follow. And we wanted to use argument buffers, and it was very hard to convince ourselves to like spend months of work on SPIR-V cross in that sense. So we didn't do it, and we were slowed down by this. Some of you may say that, okay, why are you telling about the slowness of shaders if there is a pipeline cache and it's going to save everybody? Short answer is sure, there is a pipeline cache. There are different mechanisms in D3, D12, and Vulcan to cache intermediate results of your pipeline, or not intermediate, some reusable blobs of the pipelines. They are complicated. They are hard to use, and they are not going to help your first run in any way. So I think doing it fast is still important. So existing solutions such as GLSL, Shader-C, and SPIR-V cross are okay. You can get probably 80% your way down there, but not the other 20%. It has the a lot of gotchas, limitations, like everything has to go through SPIR-V cross. You have to have Vulcan SDK installed and so forth. So I think we can do better. Let's proceed to part 2 of the talk, which is what can we do better? Project Javelin started in like 2019 as an attempt for us to use SPIR-V as an intermediate representation for generating all the shaders ourselves in Rust. We thought it's a great format. We wanted to use it. And like the fact that it's binary and standardized, it's really inviting to sort of mess with it in Rust. We started learning about SPIR-V consequently. And the first stage was denial. we thought it's great. So we choose our SPIR-V as a library that implemented Rust, and it's still actively used as a basis for our translation layer. And we contributed a lot of changes to make it one of the layers that they represent SPIR-V, to make it usable as an intermediate representation. So after 35 pull requests and like a whole summer of work, it was still not nearly there. Maybe it's our fault. I can admit that, but we weren't able to get it there. It was still a mess. We tried to do that. It auto-generated those layers, and we tried to adjust the auto-generation so that the result of it is a usable IR, and that was failing. So then came depression. We realized maybe we are not doing a good thing, and moreover, we started having doubts over whether SPIR-V is the right thing here, is the right middle link in the chain of translation. So later on, this is like 2 years from there, I published an article about the horrors of SPIR-V, and like everything is wrong with SPIR-V. And I concluded that it's a great format for drivers, but it's a bad format for intermediate representation for us. And that's a very controversial statement. I'm happy to talk about that. So some of the biggest issues. It has this wonderful thing called multiple entry points. You can have a single shader module with hundreds of different entry points for different stages. And you can use those entry points from the same module in different pipelines. It's great. It sounds amazing. And that's what everybody needs. The only problem is there was no use of it, because everybody was at first used GLSL to compile SPIR-V, and GLSL only knows about the single entry point. So all the SPIR-V that went through the drivers, that went through the testing suite that they had, all of them had a single entry point. They didn't expect anything else. Then there appeared to be a GLSL to SPIR-V translator that takes C from Microsoft. And it sounded great because HLSL has multiple entry points. So why don't we use them? I don't know. I filed an issue. They said they're not interested and that we are going to support a single entry point. So even the XC only supports a single entry point today, which means all of the SPIR-V in the wild, outside of maybe some of the web GPU stuff, have a single entry point. And our attempts to use multiple entry point failed miserably, crushing into reality because bugs. Drivers, lots of bugs. NVIDIA has bugs, AMD has bugs, mobile vendors has bugs. Nobody likes that because nobody tested with that. And that is an epic failure, not ours, but the standard that allowed multiple entry points as a feature that's not tested, I think. Then if you are looking for something in SPIR-V, good luck, because there is a SPIR-V itself. There is also GLSL extended instruction set, which everybody uses in a separate document. And there is an environment specification for SPIR-V inside Vulcan, which is a part of the Vulcan spec. So if you know all these three parts, you're probably have a high chance of figuring out an answer. If you're not fluent in them, then good luck finding the parts that answers your question. Like, how do you access out of bounds of an array? And try to find an answer in any of those. Finally, the control flow representation in SPIR-V is very complicated. I want to say it's terrible, but it's probably not. But we natively, SPIR-V represents your control flow as a graph of nodes, and it uses the dominance semantics to know how the control flow is shaped. This is nowhere near the way people think about control flow, and nowhere near the other languages represent control flow. So you have to reconstruct the structure, like what is a loop, what is a condition, based on the blocks that are in that SPIR-V, if you're using SPIR-V as an intermediate representation. And someone may argue that SPIR-V has this wonderful merge instructions that are supposed to show you the structure of your control flow, and they are required in the shader capability. So to our surprise, the merge blocks are making it easier, but not completely easy. You can still face a number of situations where they are not matching what you want for the structured control flow. Like they are only halfway, they're getting you halfway there, and the other halfway you have to figure out yourself. So representing control flow in the way SPIR-V does it is great for the drivers, not so great for generating MSL or HLSL or GLSL or anything, basically, that's human readable. All right, so 2020 comes, and WebGPU group, after years of discussions, finally makes progress on the WebGPU shaping language. It's called WGSL for WebGPU shaping language, and it appeared out of Google's proposal for which it was called TEMP, just like the implementation today that they use. And they wanted a textual representation of SPIR-V basically to be standardized. And the group agreed to take it as a starting point. And then the starting point began to evolve. So very quickly, WGSL stopped being a like textual representation of SPIR-V and became a thing on its own. And now it's not merely SPIR-V. But the good thing is it was actually designed to target other languages. So it is very sane. It is very nice to write infrastructure around, unlike SPIR-V. And by sane, I mean, it defines strong semantics. Like if you're rounding something, it says which way it's rounding. It doesn't leave a lot of wiggle in the spec. This is an example of WGSL code. It defines 2 entry points. I said the multiple entry points are great. So WGSL does support that. It's the vertex entry point on the top and fragment entry point on the bottom. And notably, the inputs and outputs, the pipeline inputs and outputs are represented as functions, function arguments, and result types, which I think is very nice. So syntax is a bit unusual, but you may notice that the function definition looks very much like Rust. And I think that's a good thing. Here comes the project that we started right when WGSL was announced. It's called Naga. It's basically an attempt to just write the translation infrastructure without basing on anything. Like previously, Javelin was trying to base on RSPIR-V and the SPIR-V intermediate representation. In Naga, we just wanted to get stuff done, basically. And we took what was in the WGSL draft there and mixed it with the SPIR-V specification to get a starting point for our intermediate representation layer. We wrote it from scratch. In the first front ends were WGSL and SPIR-V, and the back ends were Metal and SPIR-V again. It followed the following principles. First, it had to be pure Rust. It had to use very cache-friendly data structures, and it had to be completely safe. We also want panic-free. It shouldn't panic. Instead, if something goes wrong, we should return an error. What makes Rust shine there? I think number one by far is just enums. Building your intermediate representation with enums is such a joy. It's unbelievable. Like you can, it's exhaustive matching and associated value typing. Like option instead of the void star in C++. It makes compiler tech really nice to write for. Then, because shader infrastructure is very self-contained, it's natural to write a lot of tests in it, unit tests, integration tests, everything. We can do it easily with Rust. Documentation is also nice in Rust. So if you look at the IR definition file in Naga, it's half of the file is comments, doc comments. And I think we can do more. Now, this is the most interesting thing I think about Rust. Jim Blendy quoted that Rust forces you, because of the ownership rules, to think simple. I think it's very important. How do we achieve cache friendliness? All the things that we do is essentially structure of arrays. And these arrays are only growable because when you are parsing the module, you only add stuff to your intermediate representation. So the scheme shows an array of types and array of constants, and a type of array references both the base type f32 and the constant 4. And the constant 4 references another type, u32, because that's the type of the constant. So that's an example. Storing them in the array and just indexing makes it super fast. Also, whenever we need uniqueness, we take advantage of index map. It's a very interesting library. It's like a map, but it gives you stable indexes. So you can access in like an array, basically, if you want to. And we strive to minimize heap allocations. There is a few, but we want them to be minimal. It's structured as LLVM in a way that there are different front ends and different backends. Everything lives so far in the same repository. The front ends are Wixel, SPIR-V, and GLSL. We generate the intermediate representation from them. Then what happens is we have to run some sort of validation on that IR. And the validation produces some of the derived information. So it's important to understand what this is. If you have an expression like y equals x multiplied by 2 plus 1, then if you look at it in SPIR-V, then every step in that expression will be associated with a separate type. It makes SPIR-V very redundant, but explicit, that everything has a type. But those types are in 99% are completely redundant. You can figure them out from the expression itself. So what we did is that they make them 100% redundant, and we make them not stored in the IR itself. So whenever you pass through validation, it generates these types for you that you can use, but otherwise they're not in the IR. So if you modify the IR, you don't need to also modify those associated redundant information. And from that information, we can generate a whole bunch of different things. We can generate Wixel, SPIR-V, MSL, GHLSL, GLSL, and even GraphViz dot files. We have to parse GLSL and Wixel. So we tried different approaches. I started with PEST originally, and I thought that it takes care of part of the problem, and it forces you to split this responsibility between what you define in PEST versus what you define implicitly with your code outside of PEST. And this division just didn't settle with me at all. So I figured that just writing the recursive descent parser myself is not that much difficult, but it gives you full control without splitting responsibilities. And it allows the errors to be nicer too. Similar situation was for GLSL frontend. It was fairly painful. It was rewritten like 3 times, but in the end, we concluded that just a handwritten recursive descent is better. Our testing infrastructure is basically defense in depth, which many different tests on different levels. But the interesting thing is the snapshots, because we are not trying to convert everything into everything. I think that would stress some of the front ends and backends more than others. Instead, we use Wigzell as the central piece. So we do anything to Wigzell for testing frontends. So you test the front end and then you check your Wigzell by eyes and see, oh, is that what it meant to be? And then in order to test backends, you take Wigzell files and you send them through each of the backends. So Wigzell becomes the central piece. Why? Because our intermediate representation is very close to it. It's like a subset of Wigzell. And that gives Naga an interesting property that you can observe basically the intermediate representation by eyes and tweak it because it's just the Wigzell code. Naga is architectured to separate expressions from statements. So statements are used to define control flow, like a statement of a switch, for example, and mutability, like a statement of assignment. And everything that is not tied to control flow and not changing values are expressions. So some statements use a lot of expressions and they can emit expressions. For example, an assignment statement would use the expressions for both left and right part, but a function call statement would use the expressions for arguments, but it would emit the expression for the result, which can be used for other things. And this is the GraphViz rendering of a simple compute shader. You can see the gray at the right, the gray blocks are statements, emit, store, I don't know. And the yellow ones are expressions, and they reference each other. It's also very nice to be able to generate GraphViz and just look at the things sometimes. Okay, where are we now? We are at the stage where we can write Wigzell shaders or GLSL, because Naga also can parse GLSL. And we can run them everywhere. We can do so without any C dependencies or any big issues, really, because everything can be done by Naga. The only problems that we anticipate to hit is the lack of chain rule polish, because it's all very new technology. And maybe some features are going to be missing too. For example, if you need arrays of bindings, this is something that we are probably going to add very soon, but right now it's not supported. So we're growing the feature set and we're reaching the level of polish that is acceptable for wide usage. And a lot of people are already using it to success. So let's look at those. Gecko, that's something I do for work. And since I lead web GPU effort, I wanted to run everywhere. And for a long time, the implementation in Gecko, which is WGPU, it used SPIR-V cross to anything. And we switched it around, I think, August or September, to use Naga exclusively. So this is what changed. This is the installer size for the whole Gecko browser. And you may not understand how complex this beast is. It's extremely complex. And we're talking about one little API, which is WebGPU, and one little thing in it, which is the shader translation. And you see this drop at the right? This is like 1% of the total installer size. So it's huge, basically. It's almost a megabyte. A lot of things are changed in this commit, but the main thing that's dropped is SPIR-V cross. So I attribute this mostly to removal of SPIR-V cross. Then goes Valorant, the most complex game in Rust, I think, today. They tried to replace shader C with Naga, and it almost succeeded, but they had to revert it. We're going to work with them to get it back. I hope we're going to get it back, but they're almost there. Another project is Vangers, which is the my project, which tries to render the old game from 1998 using a multitude of different semi-advanced GPU techniques, because it uses the fancy voxelized terrain. And I rewrote all the shaders, including the ray tracing shader, to Wixel recently, and that allowed me to actually redistribute the binary finally and have it be building seamlessly for all the users who wanted to run it. Another interesting example is the NoClip website, which runs different console games on the web, and they ported their implementation to WebGPU recently, even though WebGPU is not stable yet. But their shaders were GLSL, and they were runtime generating the shaders. So how do they port in this case? Naga to rescue, because with Naga, they can parse GLSL and spew out Wixel to feed the browser. And they can do it at runtime, because Naga is just a Rust library, which is fairly easy to just compile to a WASM module. So without any super complex preparations, they were able to do that. They contributed a number of fixes for which we're eternally grateful. And now, instead of GLSlang, which was more than a megabyte WASM file, they use Naga, which is just half a megabyte WASM file. But an important thing here is that GLSlang by itself is not solving your problem. It's only giving you SPIR-V. And if you need to run on WebGPU, you don't need SPIR-V, you need Wixel. So technically, they would need to compare Naga to GLSlang plus something that generates Wixel. So it's just half of the equation. Think like 2 megabytes versus 0.5 efficiently. And they were able to do that, and that's how their website works on WebGPU. Again, Geofx portability that I mentioned, we did the tests somewhere recently on pure Naga implementation on Dota again. And we figured that strangely, the numbers were hugely different. So the time spent in pipeline creation was dropped by a factor of 4. And I'm talking about the whole pipeline creation. I'm not talking just about shader translation. I think this is amazing. We effectively shaved off a few seconds of Dota launch on the real system. Too bad they didn't consider including our library, but well, who knows? So here comes the takeaway from the whole story. SPIR-V isn't a good intermediate representation, I think. And the tools around SPIR-V aren't perfect, even though there is a big following to them. We have a lot of fun writing Rust things around shaders, and we can do better. We're almost there. Also, you don't have to use SPIR-V or GLSL. There is also Wixel now, which is an interesting thing to consider. Note that I didn't talk about the GLSL at all here. I know that some people use GLSL to generate SPIR-V and go from there. I think largely the same concerns apply to that toolchain that I mentioned about GLSL-C and SPIR-V cross. So this is some of the things our community members made. Goodbye Shader C, hello Naga. And I would like to thank our contributors and the early adopters in particular. And thank you for bearing with me in this late hour. So that's pretty much the end.